In this lesson, we'll look at chemical bonding. First, let's look at what are chemical bonds. Well, all chemical bonds are electrostatic forces of attraction between a negative and a positive. And we'll see how is this when we look at the three major strong bonds, which are the metallic bonds, ionic bonds, and covalent bonds. Metallic bonds. Metals exist as a giant metallic lattice structure. It's a lattice structure because it's a regular arrangement of all the cations. The metallic bond is the electrostatic force of attraction, same for all bonds, between the positive metal cations, in this case we have Ca2+, and the negative C of the localized electrons. So how do we represent the structure of metallic bonds when we draw them? Well, first of all, we draw the metal cations in a regular arrangement. In this case, I've drawn Ca2+, I draw 4 of it, and then I draw the C of the localized electrons and label it. Since I have 4 Ca2+, I should have 8 electrons, which are drawn here. Notice the electrons are not drawn in regular arrangement, but the cations are. Let's look at some of the properties of metals and the metallic bond. Well, firstly, the metallic bond is a non-directional bond, meaning that the metal cation is attracting all the electrons that are near to it. The properties of metals. Metals have high melting point, boiling point, and are hard. And these three properties can be explained by the strong metallic bonds present, as well as a giant metallic lattice structure, which requires a large amount of thermal energy to break them up. Well, metals are malleable, which means you can hammer them into shape. Why are they malleable? It's because of the way the cations and C of the localized electrons are attracted to each other. When we apply enough stress to this part, it shifts. But notice, the metallic bonds are not broken. Therefore, the structure still remains attached to each other. It just has moved. Well, metals are good electrical conductors and thermal conductors. They're good electrical conductors because when you apply a voltage, the delocalized electrons in the C of delocalized electrons are charged and they can move from the negative electrodes to the positive electrode. They are good conductors of thermal energy because on heating, the mobile electrons can actually transfer the heat very fast. They have definite luster, which means they are shiny, and this has to do with the properties of the electrons present, whereby they can emit the light that is shining on it. Metals are soluble in one another, and that's how we form the different types of alloys. Let's now look at ionic compounds. Ionic compounds exist as giant ionic lattice structure. That's their structure. So what is an ionic bond? It is the electrostatic force of attraction between, in this case below, the Ca2 plus cation and the O2 minus anion. So when you are mentioning it, you should also mention what is the cation and what is the anion. How do we represent the structure? It's as follows, where we have the positive and the negative, they are drawn in alternate manners. Let's look at ionic compounds now. Now, ionic compounds have cations, which are the positive ions, and the anions, which are the negative. Your cations are mainly your metal cations, So a group 1 metal like sodium will form 1 plus, group 2 like calcium form 2 plus, and so on. The only non-metal cation that you expected to know is the ammonium cation, which is a NH4 plus. Notice NH4 plus doesn't really have a metal in there. Now what about the anions? Well, let's talk about two types of anions. First, you have the monoatomic, which means that anion consists of just one atom. So in this case, we have chlorine, which has gained one electron. It now forms the chloride. Sulfur will form the sulfide. Nitrogen will form the nitride. Cl is 1 minus because it's a group 17, so it requires one extra electron to reach the noble gas structure. Sulfur is group 16, so it requires 2, and so on. Now, apart from this, we have your polyatomic anions, which you are required to remember. They are given here. They include the hydroxide, OH minus, nitrate, NO3 minus, carbonate, CO3 2 minus, sulfate, and phosphate. Now, if you want, you can also remember the ITE, for example, nitrite, sulfite, and phosphite. Now, what's the difference between the ITE and the ATE? Well, the ITE is less one oxygen. So instead of NO3 minus, now the nitrite is NO2 minus. Sulfate is SO4 2 minus. The sulfite is SO3 2 minus. Phosphate is PO4 3 minus. Phosphite now becomes PO3 3 minus. Now, ionic compounds are named based on the cations and anions. For the cation, we just leave the name as it is. For the anion, then we have to follow the charge of the anion. Now, there are two types for the non-transition metal. Transition metal are the D block. If you look at your periodic table, you have your S block, D block, and your P block. So the ones in the middle are your transition metal. So for non-transition metal, we name them based on just put the metal and then the anion. In the first case, I have Na. Na is Na plus, so that's sodium. Cl minus is chloride, it forms sodium chloride. K plus, potassium ion. PO4, 3 minus is a phosphate, so it's called potassium phosphate. Notice I do not write how many potassium is there. Okay, why? Because if you have K plus, we have PO4, 3 minus. It's only natural, we should know there should be K3, PO4 to balance the charge. Now for transition metal, it's slightly different because they can form more than one oxidation state or charge. For example, Fe, you have Fe2 plus, you have Fe3 plus. So there's a need to identify which one is being used. So let's look at how to name it. FeSO4. So you FeSO4. SO4 I know is 2 minus. Therefore, in this case, I know this Fe is Fe2 plus. So this is called iron 2 sulfate. Now let's look at the second one, Cu2O. So O I know is 2 minus. So in this case, I know I have Cu plus and Cu plus. So that's called copper 1 because copper 1 plus oxide. Now let's look at the properties of ionic compounds and ionic bonds. Ionic bonds are non-directional in that the metal cation attracts all the nearby anions and the anions attract all the cations as well. They have high boiling point, high melting point, and are hard or rigid. This is because the strong ionic bond requires a large amount of thermal energy just to break them apart. They are brittle because, notice, if I just shift the ions by one position, the like charges are now next to each other, they will repel, and therefore it will crack. Ionic compounds conduct electricity in a molten or aqueous state. Molten means it's melted. Aqueous means we dissolve in water. In the solid state, the ions, although present, they are in fixed position and therefore they cannot conduct electricity. But when they are molten or in aqueous state, they can move around freely, therefore they can conduct electricity. They are soluble in water and polar solvents because they can form ion-dipole interactions. So notice in this case, NaCl breaks up to form the Na plus and Cl minus. So the Na plus and Cl minus are the ions. The dipole is the one caused by the water. One part is more negative, one part is more positive. Notice for the Na plus, the negative part of the water is pointing towards it. And for the Cl minus, the positive part of water is pointing towards it. Because as we know, all bonds are between a plus and a minus. Now you try yourself, write the following chemical formulas. You should stop the video here and continue after you have finished. The first case, we have sodium carbonate, Na plus, CO3 2 minus. So to balance the charge, I need 2 of Na, Na2CO3. Calcium nitrate, Ca2 plus, NO3 minus. To balance the charge, I need calcium and 2 of nitrates. In this case, I have iron 3 plus, and hydroxide is always a minus, so this forms EOH3, and ammonium phosphate, I form NH4 3. Now you try to explain why calcium chloride has a high boiling point with reference to structure and bonding. Continue after you have finished. This question requires both structure and bonding. So what's the structure? So I write CaCl2 exists as a giant ionic lattice structure. Alright, now how do I explain high boiling point? So high boiling point means you require large amount of energy is required to break the strong ionic bond between the calcium 2 plus and Cl minus ions. Therefore, the boiling point is high. And that's how we answer it. So we mention the structure because it asks for the structure. We mention the bonding and what is it between. And then we conclude. Now let's learn how to draw dot and cross. For drawing dot and cross, I'm going to look at two types. One for ionic compounds. One is monoatomic ions. For example, something like NaCl, right? K2O, something like that. Okay, how do you draw it? Well, firstly, we should know that the metal cations have lost all their valence electrons. So, Na will form Na plus. We only draw the valence electrons, so in this case, there are no valence electrons. Then Cl is minus, but Cl has its valence electrons. It has 4, 5, 6, 7 valence electrons. It's minus means it has gained one additional electron. We use a different symbol for the electron, and that's NaCl. K2O, I'll write it as 2K plus, and then O, 2 minus. O has got 6 of its own electrons, 2 additional electrons taken from potassium, and that's how it looks like. The drawing of polyatomic ions will be done after we have finished the covalent bonds. Now you test yourself how to draw magnesium chloride and aluminium oxide, and we'll continue after you have finished. Pause it here and start again after you have finished. Now magnesium forms Mg2 plus. So magnesium is Mg2 plus Cl minus, so it forms MgCl2. So I have 2 of Cl and 1 additional 1 electron. So that's magnesium chloride. Aluminium, Al3 plus, O2 minus. So it's Al2O3. So I have 2 Al, 3 plus, 3O, 6, and 2 other electrons, 2 minus. And that's how we draw the dot and cross for ionic compounds. Now let's look at covalent substances. So there are two types of covalent substances. One is a giant covalent structure, and one is a simple covalent molecule. So for giant covalent substances, the covalent bond predominates the whole substance, means everywhere there is just covalent bonds. Examples like graphite may have instantaneous dipole-induced dipole as well. Others like diamond, all that are just covalent bonds. Now simple covalent molecules are slightly different. The covalent bonds hold the atoms together, but the molecules are then attracted based on the intermolecular forces, which we will talk about later. Let's first look at the giant covalent substances. So what is their structure? Well, they exist as giant covalent lattice structure. And the covalent bond is the electrostatic force of attraction between the positive nuclei of both atoms and the negative shared pair of electrons. So this definition for covalent bond is independent whether it's giant, whether it is simple covalent molecule as well. You're expected to know 4 different types of giant covalent substance, which is diamond and graphite, which are just carbon, silicon, and silicon dioxide. So that's carbon, silicon, silicon dioxide. So these are the structures which you need to know how to draw and to recognize them. So graphite are mainly hexagonal rings forming plates, and between each plate is your weaker instantaneous dipole-induced dipole interactions. Diamond and silicon are exactly the same, except diamond is carbon and silicon is silicon, right? But they have the same structure. Each atom is joined to another 4 atoms by covalent bond. SiO2 has slightly different structure, where each Si, the blue ones, are joined to 4 oxygens, and each oxygen is joined to 2 Si. So what are the properties of graphite? Well, they are soft and slippery because although the covalent bonds between the carbon atoms in the plate are strong, but each plate can then slide past each other because of the weaker instantaneous dipole-induced dipole interaction. They conduct electricity because the electrons are delocalized along the planes, and these electrons can act as a mobile charge carrier. So this is one thing unique about graphite compared to the rest of the covalent substances. Graphite is insoluble in water because it cannot form very strong bonds with water. They have a high melting point because large amount of energy is required to break the strong covalent bond. Diamond is hard. Why? Because they have strong covalent bond throughout the structure. They are insulators of electricity because they don't have any charge carriers. They are insoluble in water because they cannot form strong bonds with water. And they have high melting point because they have strong covalent bonds which require a lot of energy to break. This is also the same for silicon and silicon dioxide. All these properties. Now let's go to simple covalent molecules. Simple covalent molecules have a discrete molecular structure, that is their structure. The covalent bond we've covered before is exactly the same. Now why do they have low melting point and boiling point? It is not because of the covalent bond. Rather, it's because of the intermolecular bonds, forces of attraction, which we will cover later. Now, how do we name covalent compounds? They are based on the atoms present. For binary compounds, which contain two types of atoms, which is the main ones that you will be doing, the less electronegative will be placed first as an element, and the more electronegative will be mentioned last as a IDE. For example, P2O5. So I have two phosphorus. Oxygen is more electronegative, so it's considered the oxide. So this has two phosphorus, so it's diphosphorus, two phosphorus, five oxide, so pentaoxide. Well, the covalent bond is strong and is directional. Yeah, exactly pointing in a fixed direction, and this gives us the shape of the molecule. They have low melting point and boiling point. This is because of the weak intermolecular forces, either the instantaneous dipole, induced dipole, permanent dipole, or hydrogen bond. But to understand which of these bonds interactions or bonds are present, you will need to first know the polarity of the molecule. But to know the polarity of the molecule, you need to know the shape. And to know the shape, you need to know the dot and cross. So let's start with the dot and cross. Now I'm going to teach you an easy way to draw a dot and cross. But first we shall split it into three types of covalent molecules or covalent ions. Okay, so one is a neutral molecule, so it's uncharged. Second one is negative ions, and third one is positive ions. For neutral molecules, the first thing we need to do is to place the atom. So in order to place atoms, you need to know which one is in the center. Okay, we take the less electronegative ones to be the center. Then we add electrons. Then we form bonds. And then we calculate the number of electrons in the center atom, and to see if we need to make double bonds to dative bonds. How we'll do this? Let's continue. Let's look at this case, sulfur trioxide. One sulfur, three oxide. So the name itself does tell us. Sulfur is less electronegative, oxygen is more electronegative. So sulfur is in the center, oxygen is at the side. Okay. Next, I need to add in the electrons. Now, can add in the electrons. Let's see. Oxygen has got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Sulfur has got 1, 2, 3, 4, 5, 6. Now, oxygen has 6. In order to form a stable compound, you would like to form 2 bonds to make 8. So I rub off 2 from oxygen, 2 from sulfur, and then I will make it have the double bond. I do the same for the oxygen on the top. And from the side, next, I like to evaluate the number of electrons in the central atom. So looking, you see the side atoms always have 8. So there's no need to consider about them. We'll look at the center. Now in the center, now I have sulfur has got how many atoms? Sulfur has got how many electrons? 4, 5, 6, 7, 8, 9, 10, 11, 12. In this case, because sulfur is in period 3 and below, it can use your d orbital, so it can have more than 8. So for such cases, we'll just leave it as it is. So this is SO3. Dative bonds only need to be considered when you are considering the center atom from period 2. Now let's look at water. Why don't you try yourself first, and then we'll continue. So water, now water is slightly different. Why? Because oxygen has to be in the center. That's because hydrogen can only form one bond. So hydrogen always forms at the side. So in this case, I know hydrogen would form one bond. Oxygen has got 6 electrons, 1, 2 shown, 3, 4, 5, 6. Then I look at the center atom oxygen, I see how many electrons? 8. Just nice. So for dinitrogen monoxide, we first write it, and 2O dinitrogen monoxide. So from the name, I know nitrogen is in the center. Oops. Now I know oxygen is group 16, so it needs 2 bonds. So let's make 2 bonds. Nitrogen is on the left hand side, needs to form 3 bonds because it's group 15. Put in the other electrons. For oxygen, I need center nitrogen already has 5. Nitrogen on the left needs 2 more. Then I evaluate the center. In this case, I see there are 10 electrons, which is too many. For period 2 elements, they can have only maximum of 8. So I'm going to convert one of the double bonds here to a dative bond. I shift back the 2 electrons. And I convert the bottom one to a dative bond. And that's the final answer. Now you try yourself to draw the following for ammonia, iodine trifluoride, and nitrogen dioxide. You continue after you have finished. Okay, ammonia is NH3, iodine trifluoride, nitrogen dioxide. So NH3 is NH. Hydrogen forms one bond. Nitrogen got 5 electrons, 1, 2, 3, 4, 5. Looking in the center, nitrogen has 8, so that's correct. Iodine trifluoride, iodine, fluorine, fluorine, fluorine. Fluorine is group 17, so it needs one bond. Fill in the other electrons. Iodine has got 7, 1, 2, 3, 4, 5, 6, 7. And that's iodine trifluoride. Nitrogen dioxide. Oxygen forms 2 bonds. Oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. 4, 5, 6. Nitrogen got 5. Now I see nitrogen now has got 9. So that's not right. So let's convert one of the double bonds into a dative bond. We shift back the electrons. We make that to a dative bond. In this case, nitrogen has 7, right? Which is okay. So it's a very unique thing for nitrogen. Sometimes because of the unpaired electrons, it will only have 7 instead of 8. Now we're going to look at how we do for negative ions. So the first part is almost the same. We place the atoms. Then we add in the electrons. We add in additional electrons corresponding to the charge. But how do you do this? 1 electron to each of the outer atoms, as many as you need to reach the charge. After that, we form the bonds. And then we evaluate the center again. Let me show you for nitrate. So nitrate is NO3 minus, oxygen, 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 oxygen. Oxygen likes to form. So first of all, let's just write the electrons. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5. Now, nitrate has got 1 minus, so let's give 1 more electron to any of the oxygens. Let's say I give to the one below. Okay, so because the one below now has 7, it only wants to form 1 bond. So let's just write it off. Okay, so it only forms 1 bond. Well, so 2 the other side needs to form 2 bonds. And that's nitrate minus But before we finish, we always need to look at the center atom. Now in this case, we see the nitrogen has got 10 electrons. So that's not possible. So let's convert one of the double bonds to dative bond. I remove the oxygen electrons, give it back, and then I convert the one on nitrogen to form the dative bond. And that's NO3 minus. Now you try for sulfate ions and phosphate ions. Sulfate is SO4 2 minus, phosphate is PO4 3 minus. So sulfate SOOO. Now 2 minus, let's just give it to 2 oxygens. So in this case, those 2 oxygens only want to form now 1 bond. The other 2 needs to form 2 bonds. Then after that, I'll draw in all the other electrons. So the oxygen is 6, 5, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Don't forget that minus is actually just one additional electron. And then 1, 2, 3, 4, 5, 6. And that minus is just another electron. And then we put the charge outside, 2 minus. In this case, because sulfur is group period 3, I don't really have to care how many electrons in the center. So that's the structure. Phosphate, PO4 3 minus. So which means 3 of this oxygen now only forms 1 bond. And the other oxygen forms 2 bonds. Then you fill in the rest of the electrons. And then we put a bracket and put in the charge. And that is phosphate. Now, how do we do positive ions? Now, positive ions are those that normally have H plus joined to it. So we remove one H plus first from the formula, and then we do as per normal. And when we finish, we add the H plus to the lone pair. Let me show you what I mean. For ammonium, this is NH4 plus. This is NH3 NH plus. So first let's draw NH3. N, H, H, H. One bond, one bond, one bond. Sorry, let's see this. Okay, so that's it. Now I'm going to add a H plus to this. So the H plus joins to the lone pair. H plus does not have any electrons on its own, so it just joins to the lone pair, and therefore we have a dative bond. Let's just convert that to a dative bond to make it look nicer. That's NH4 plus. Now you try for H3O plus. Continue after we have done it yourself. So H3O plus is same as H2O and H plus. So I first do H2O. And then I add H plus to any one of the lone pairs and make that become a dative bond. And we have H3O plus. Now let's talk about valence bond theory. Now valence bond theory tells us there's two types of overlap. One is a sigma bond, which is a head-on overlap, and next is a pi bond, which is a side-on overlap. So the sigma bond is the first bond that is formed between any two atoms. So if it only has one bond, that's a sigma bond. If it has two bonds, the first bond is a sigma, second bond and onwards are all pi bonds. So a sigma bond is a head-on overlap. So any orbital can be used to form a sigma bond. The pi bond is every other bond apart from the first bond. So if it is two bonds, a double bond, then one bond is sigma, the other one is a pi. If it's a three bonds, triple bond, like nitrogen, you have N triple bond. So one sigma and two of them are pi's. So s orbitals cannot be used to form pi bonds because they require a side-on overlap from the sides. But your s orbital, which is round, cannot form bonds to the side. So let's calculate how many sigma bonds and pi bonds are there in the following molecules. So you calculate first, and then after that, we'll continue here. Okay, let's count how many sigma. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 sigma. There's a double bond here, so that's 1 pi. For the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sigma, and this one is 2 pi. So the first bond is a sigma, and all the other bonds joining the same two atoms are pi bonds. Now earlier part I promised you we'll go into shapes, but how do you go to shapes? So the valence shell electron pair repulsion theory predicts the shape of the molecule. But perhaps it's better to just, if I were to call this actually the shape around the central atom. Why? Look at the one at the right. What shape would you put that? I would consider that a shape of a dog, maybe a shape of an animal, but no. So it's actually not looking at the whole molecule, it's just looking like, say for this guy, for this A, what's the shape around A? What's the shape around B? What's the shape around C? So that's the shape we are looking around a particular atom, not overall. So this theory is based on the fact that all electron pairs, whether they're bond pairs or lone pairs, they will try to be as far apart from each other as possible. Now, one of the things we need to remember is that this bond pair, as used in the VS-EPR, only considers the sigma bond. So this is the first shared pair between two atoms. So the pi bonds are not considered bond pairs. They're just ignored in this theory. For the lone pairs, these are electron pairs on the central atom which are not shared. For example, let's look at CO2. So COO. Then oxygen from two bonds. And that's CO2. So how many bond pairs do I have? 1, 2. Remember, only the sigma bonds. So 2 bond pairs. How many lone pairs? Now, oxygen has a lot of lone pairs, but it's only around the central atom. So you look at carbon, do you see any lone pairs? No. So this is 0 lone pair. So in this case, it's 2 bond pairs and 0 lone pair. So then how do we know the shape and angle? So this now we had 2 bond pairs, 0 lone pair. That should give us a linear. So CO2 is linear. And the angle is 180. Now if I have 3 bond pairs and 0 lone pairs, then it's a trigonal planar. Angle is 120. So you need to remember all of those shown here. They are also found in your book. So now let's look at the shapes and angles around the central atom for water, sulfate ion, and nitrogen dioxide. You try it first, then continue. Water is H2O. So if you drew it right, it should look like this. So let me count. 1, 2, 2 bond pairs. 1, 2, 2 lone pairs. So 2 bond pairs, 2 lone pairs should give me bent 105 degrees. Now sulfate, SO4 2 minus. So if you drew it correctly, it should look like this. 2 of the oxygens have minus, so they form 1 bond. The other 2 are not charged, so they have 2 bonds. Write in the other electrons. And that's it. 2 minus. So looking at sulfur, I have 1, 2, 3, 4 bond pairs. And 0 lone pair. So this should tell me this is a tetrahedral, 109 degrees. Nitrogen dioxide, by this case nitrogen has too many, so let's convert one of the double bonds to be a dative bond. Then let's count. 1, 2. There's 1 electron there, but we'll still consider this as 1 lone pair. So 2 bond pairs, 1 lone pair, this should give me bent 118 degrees. Next thing, before we can consider polarity, we look at electronegativity. Now, electronegativity as an atom determines the ability of the atom in a covalent bond to attract the shared pair of electrons. So, if it's more electronegative, it will pull the electrons on an average closer to itself. And that part will be the more negative part of the molecule compared to the other part which is less, the other atom which is less electronegative. For example, if you have HCl, Cl will pull the electrons closer to itself. So this part will be slightly more negative, and hydrogen will now be slightly more positive. So in order to determine whether the covalent bond is polar or not, we need to determine whether there's a difference in electronegativity. For simplicity's sake, we consider any two atoms of different elements to be polar except C and H. What do I mean? That means a CH bond is considered not polar, right? A CC bond, they are same, not polar. What else is not polar? Br2 is not polar, I2 is not polar, S8 is not polar. Why? Because they have the same type of atom. So then what's polar? HCl is polar because different atoms. HBr is polar. IBr is polar. Right? H2O is polar because they are also different. So the bond itself is polar. Now to understand whether the molecule is polar, we need to consider two things. One, are there polar covalent bonds? So if there are no polar covalent bonds, then the molecule is non-polar. For example, C2H4, is it polar? Now, judging there's only carbon and hydrogen, definitely the bonds are not polar, so this molecule is already not polar. We don't need to consider the next. And then you can have things like Br2, same atom, not polar. H2, not polar. Now, if the bonds are polar, we then need to consider whether the dipoles will cancel out. So what do you mean by dipoles will cancel out? Well, another way to look at it is that the molecule is not symmetric. The molecule is symmetric if the outer atoms are not identical, then it's not symmetric. Or the shape is not symmetric. Now what shapes are not symmetric? Bent and trigonal pyramidal for your level. So let's try that on, let's look at ammonia. N, H, 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 right? So N and H, are they the same? No. So in this case, the bonds polar. Now, is the molecule symmetric? Okay, so in this case, it's either if the outer atoms are different. If they are same, it's symmetric. If they are different, then they are not symmetric. In this case, they are the same, so we cannot use that. Now let's look whether the shape is symmetric. In this case, I know it's a trigonal pyramidal. So being trigonal pyramidal, I know it's asymmetric. So the bonds, the dipoles will now not cancel out. So therefore, this one is polar. Why? Have polar bonds and two dipoles do not cancel out. Now you try for the next few before we continue. Next, we have HCl. Okay, are the bonds polar? Bonds are polar. Do the dipoles cancel out? No, they don't cancel out. Why? Because in this case, there's just one bond, so it cannot cancel out. So this one is polar. C3H8. Are the bonds polar? No. So the moment the bonds are not polar, we don't need to consider. So this is not polar. SO2. Okay, are the bonds polar? Yes, bonds are polar. Do the dipoles cancel out? Okay, first let's look at the two atoms oxygen. They're the same. So what is the shape? Shape is a bend. So the moment the shape is a bend, we know the dipoles can no longer cancel out. So this one is polar. So let's look at the intermolecular forces. Well, there are three types: instantaneous dipole, induced dipole, permanent dipole, and hydrogen bond. The instantaneous dipole, induced dipole is the weakest force of attraction. It's present in all molecules. Okay, it is the dominant force present when there's a non-polar. So non-polar only has instantaneous dipole, induced dipole interactions. How does it change? Now, instantaneous dipole, induced dipole interaction have different strengths based on their mass. For molecules with higher mass, they have larger electron clouds, therefore easier to distort, stronger induced dipoles, and therefore stronger instantaneous dipole, induced dipole interaction, so they have higher boiling points or melting points. Secondary factors that affect this is the shape. But don't forget, this is secondary, so this is only used if the molecules have exactly the same molecular mass. As shown below, we have C5H12. So one is linear and one is spherical. Now the straight chain one, if you think about it, it has a large area for it between both of them. The dipoles are easier induced. So we have stronger instantaneous dipole, induced dipole compared to the spherical one. Now your permanent dipole is present only in polar molecules. So when it's non-polar, it's instantaneous dipole, induced dipole. For polar molecules, they have both instantaneous dipoles and permanent dipoles as well. Now the permanent dipoles are normally stronger than the instantaneous dipoles, induced dipoles. And the strongest of the intermolecular forces is the hydrogen bond. So this is the strongest. Now this requires the hydrogen to be joined to O, N, or F. For example, if you have H2O, so you have that hydrogen, or you can have NH3, or you can have H2F, HF, right? So the hydrogen must be directly linked to either O, N, or F. And this will then attract to the next one, like the lone pairs here. It will be attracted to there. So how do we draw it? So there are a few requirements for drawing it. I've drawn here for ammonia, HF, and H2O. So first, we need to draw it out, and we need to put the delta plus and delta minus. So delta minus and delta plus. The second thing we need to show is a lone pair. Because the bond is directly pointed towards the lone pair. So you need to show the lone pair where the bond is pointing. Draw and label the hydrogen bond. Okay, so that's how we draw hydrogen bonds. How do we draw ion dipole interactions? For example, N is Cl aqueous. Well, first we split it up to the Na plus, Cl minus. Now we know water looks like this. The oxygen is minus, hydrogen is plus. So Na is plus, obviously the oxygen will point towards it. And then this is the ion dipole interaction. For chloride, of course, the more positive hydrogen will point towards it. And that's the ion dipole interaction. Now, let's test you. Can you explain the difference in boiling point between water and sodium chloride with respect to structure and bonding? After you finish, we'll continue. Well, first we have structure and bonding. So structure, what is a structure? Water has a discrete molecular structure. Sodium chloride has a ionic lattice structure. So first mention the structure. Now, what type of bonds are there? So you have strong ionic bonds between Na plus and Cl minus ions. We have weak hydrogen bonds between the water molecules. So more energy is required to break the strong bonds than the weak bonds. Therefore, the boiling point of sodium chloride is higher than water. What about silicon and sulfur trioxide? Again, pause here and continue when you have finished. Well, silicon has a giant covalent lattice structure. Do not forget it's one of the four. Sulfur trioxide exists as a discrete molecular structure. So in silicon, we have strong covalent bonds between silicon atoms. In sulfur trioxide, we have weak instantaneous dipole-induced dipole. You need to know which one of them. So sulfur trioxide looks like that. So it's 3-bond pair. Okay, so 3-bond pair is trigonal, planar. So this is not polar. Okay, then we talk about the energy, and then we conclude about the boiling point. Now you try for carbon dioxide and HCl. Well, carbon dioxide and HCl are both having a discrete molecular structure. You still need to mention it. In HCl, because it is polar, you have permanent dipole interactions between the HCl molecules. Well, for carbon dioxide, you have instantaneous dipole-induced dipole interaction between the carbon dioxide molecules. Then you can go to the energy and you conclude. And that brings us to the end of this lesson. Thank you.